Okay, guys, so we are done with the section of the Jacobian of matrix, and we observed that for the example that I solved in part 15. Let me create the volume. So for that problem, the Jacobian matrix, as I taught you, was in the 6 by 3. And if you want to calculate the inverse of the Jacobian, why? Because I told you Jacobian is relating the joint's angular velocities to the end effector angular velocity, right? Right. So if you want to do that, so if I say j minus 1 means inverse in x dot is equal to j minus 1 in j in q dot, the problem is that we don't have this, because we don't have this one, because the j here was non-square matrix for this robot. Okay, for a non-square matrix, say for 2 by 3, like as A, B, C and D, E, F, if I say matrix A, generally speaking, we don't have A inverse. That's a ridiculous joke. Okay, so for this case, I'm going to talk about the redundancy of a robot. Redundancy of a robot. Okay, of a robot. So now let me go back to our famous relation x dot is equal to, but because now you know what is Jacobian, how to calculate that, j q dot, that's right. So if I have a time derivative of these guys from both sides, gonna be x double dot, gonna be j, that is a function of the angles, as you saw in the previous class, sine of q1, sine of q2, sine of theta 1, sine of theta 2, and in q double dot plus d over dt of j of q, that's right, in q dot, first and second plus second and first, right? So obviously, guys, here this x double dot is vector of and effector accelerations, right? At the end of the day, in robotics, we do care about the end effector motions, right? And so, and this was the vector of velocity of the end effector. So now, for God's sake, I'm naming B. If this was for the vector of end effector acceleration, you see that this is gonna be joints accelerations, right? So this is gonna be this q dot is, as we know, instantaneous joints acceleration. That's right. I forgot the E here. That's right. So now I'm naming as B. Okay. So so because at the end of the day, let me show you, guys. This. So at the end of the day, if you go to my dynamic system and control lab, and let me shut. So if you go to my dynamic system and control lab, see, when it runs, come on, okay. So this is deep learning that we have done unpublished by my Alex PhD student. So the robot takes the object, and you see the obstacle, and put this object over the destination. So we know this trajectory, see this trajectory of the end effector. So we know this by deep learning. So now what we're gonna do, we're gonna, let me comes up again. We're gonna see these joints angle. So we're gonna go backward, inverse kinematics, backward, inverse kinematics. So we have the end effector motion. So we have to assign, or we have to determine the joints angles to generate such an end effector motion. Understood? So, okay. So that's why at the end of the day, in the real robotics, we're gonna find this B, right? So B is equal to x double dot minus d over dt j of q, which is function of q, your generalized coordinate system, and this. Understand? And obviously q, as you saw in the previous example in part 15, are the angles of the robot, theta 1 joints, theta 2, theta n, if you have n degree of freedom robotic system. So at the end of the day, if we want to go, this is inverse kinematics, as it is in reality, as I showed you in my lab website. Understand? So now, obviously, if you have a 6 degree of freedom robot, in the lab Baxter I showed just now, it has 7 degree of freedom. Suppose your robot in 3D space, has what? Has 6 degree of freedom. So in this case, your Jacobian gonna be 6 by n, right? Because you have 6 joints. So gonna be 6 by 6, right? So in this case, if you have x dot, our famous relation that I taught in the first class and extended to Jacobian matrix, is j in q dot. Now you can easily say q dot is equal to j minus 1 in x dot, because this is 6 by 6. 6 by 6 has an inverse, right? So why? Because the number of degree of freedom is equal to number of degree of freedom equals to the number of coordinates in the space. You have, look at here, you have x, y, z for the rigid body, and theta x, theta y, and theta z. So you have 6 motion in the space, that's right, in 3D space. In 3D space. So in this case, when you have 6 degree of freedom, your robot is not redundant. So when the robot is not redundant, you easily have inverse of Jacobian. And if I give you, if you have that, if I give you the end effector trajectory, means x and x dot, okay, so you can obviously, let me clarify for you. From the example that you have seen, let me run it for you. Look at here, guys. So again, look at this. This is another example, huh? Oh, this is my KPBS news. I'm sorry, guys. I'm talking about this. So you see that? Let me move it like this, huh? See, I'm just moving this. So I have, see, okay. So I'll run it for you again. So when it grabs it, you have x. X means displacement of the end effector. Can be x, y, x, z. But this is in the frontal plane, so it's gonna move on this plane, okay? So you have x of the end effector, right? So when you have the x of end effector, you have the velocity on the vector, because you can differentiate that, that's right? Here we go. See? So when you have inverse Jacobian, when you have x of end effector by deep learning or whatever, by desired trajectory that you do as a robotic engineer. So you can differentiate this d over dt. Then you can get x dot of tangent vector. When you have that, now you can calculate based on this relation, you can calculate q dot of the joints as what? As this Jacobian inverse and in x dot, because you got x dot from here. Look at here, let me change the color. Okay, you have the x dot from here. Okay, now you have q dot. Now if you integrate, you get the q's. Now you have desired trajectory of, these are desired trajectory of, this is not simple like that, I'm giving you the whole concept. Desired trajectory of joints to be followed by a proper controller that I was teaching on the graduate control and linear system theories, right? By proper controller, say the most simple case is PID controller. This is desired trajectories. Is it recording? Yeah, understood. Now before going to redundancy, let me teach you. Now we know that a matrix, say I'm making it general, say I have a matrix instead of J, I say A. If you have a matrix given, let me change the color, has linearly independent columns, this is the definition I'm giving you, okay? So we can calculate the so-called what? This is very important, guys, for redundant calculator. See, I'm changing the color. Left, hold on. Left pseudo inverse instead of regular inverse of a matrix, because when you have redundancy, regular inverse. So left pseudo inverse. Let me do some example. So left pseudo inverse like this. So suppose you have this matrix, guys. Suppose this is 6 by 3, like the example that we had in the previous class, but this time by the numbers, okay? 6 by 3 is 1 minus 1 3 4 0 6 and 3 0 1.5 0 1 and 4 5 6 7 1 minus 2. This is 6 by 3 matrix. You see that? On the other hand, if I go to the robotic realms, I taught you this is, you can say, oh, this is a 3 degree of freedom robotic system. That's right, because if this is Jacobian, you can say this is 3 degree of freedom system. Okay, suppose that this has a number. So look at this. If say A given has linearly independent columns, so columns, we can calculate the so-called left pseudo-inverse instead of the regular inverse. So what is the left pseudo-inverse? Left pseudo-inverse is this. Left pseudo-inverse we are showing with this kind of design plus is A transpose in A inverse in A transpose. This is left pseudo inverse of. So when that's, if I write it as this, look at here, 6 by m. So for every m is smaller than 6, okay, in robotic realm, you have to use left pseudo inverse. Left pseudo inverse. Let me go to the MATLAB. Guys, look at here. Let me go to the MATLAB. Okay, left pseudo inverse. Let me write it down because I don't have the matrix. A piece of the paper. So A is, I told you it is 2 minus 1, 3, 4, 0, 6, 3, 0, 1, 0.5, 0, 1, 4, 5, 6, 7, 8, 7, 1, minus 2. So let me play a little. So I'm saying that matrix A is 2, 3, 4 is minus 1, 0, 5, 3, 1, 6, next line is 4, is it right? 4, funny, oops, 4.5, okay, so 4.57, next line is 0, 0, 1, next line is 6, 1, minus 2. This is the matrix. As you can see here, this is 6 by 3, like as the 3D graph freedom robot that we had in the previous class. So guys, look at here. When I say linearly independency, what I'm talking about? Come on, I taught you. I'm talking about a rank of matrix, but it says linearly independent in columns, in these, right? In these, okay? So let me now look at, I say rank of this matrix. Can I? Yes, I can. It says the rank of matrix is 3, guys. And don't forget, this is very important, guys, okay? When it says in, oh, it freezes, hold on. When it says ranked out linear independent columns, means how many columns we have? We have 3 columns here. So they are, so you see that if it's linearly independent, means the column wise must be full rank. That's right. So it means rank of this matrix must be 3. If I say rank of A and it comes 2, means that the respect to the columns, that is 3 columns, it's not full rank. So it is. So in that case, the left pseudo inverse, I'm saying that A plus is equal to, as it says, it is, see here, A transpose, as we write in MATLAB, A transpose like this, multiplied by A, okay, and inverse of this. And you know that in MATLAB we are writing inverse by what? By inv. That's right. And again multiplied, as I wrote here. Look at here. I'm just writing this in MATLAB. Here we go. Okay, in A transpose. in A again transpose. This AP is now the left pseudo inverse. Because why? Because the column wise that we have 3 columns, if I calculate the rank of A is 3, so this is full rank column wise. So here we go. This is the rank of, this is the pseudo inverse. And the pseudo inverse is interesting because 6 by 3, this is 3 by 6. Now look at here, guys. This is not magic, this is mathematics. So A pseudo inverse is 6 by 3. Now if I multiply, because it's left, I have to multiply it from left side. If I multiply it by A, which is 6 by 3, result gonna be what? Do we have result? Oh, 3 by 6. 3 by 6. Result gonna be what? What to expect? Let us do that. If I multiply, see, we have 3 by 6. If I multiply it from left, AP multiplied by A, we're gonna have, yes, 3 by 3 unity matrix, like as the inverse. Remember guys? So this is gonna be 3 by 3 I 3 by 3. This means left pseudo inverse. So if your robot is working in the 3D space, and so we have 6 motions in 3D space. But if the number of the joints is less than 6, like as you have 5 degree of freedom robot, you have 4 degree of freedom robot, you have 3 degree of freedom robot, you have 2 degree of freedom robot. Okay. Now let's talk about this. Okay. Obviously, your Jacobian matrix is non-square, and if this column is linearly independent, so you can calculate a pseudo inverse of this Jacobian. Okay. So on the other hand, let me go to the next page. Let me write like this. On the other hand, if I want to summarize, for Jacobian matrix of the robot 6 by m, and your m is smaller than 6 in 3D space, so the inverse or pseudo inverse, we say, because this is non-square, you have to multiply from the left. That's why we say is left pseudo inverse, I don't want to write pseudo inverse. Gonna be I of what? I of m by m. So now, for example, here was 3, m was 3. We got I of identity matrix of what? 3 by 3. Let me go another example. Look at here in MATLAB. Suppose you have 5 degree of freedom robot. For example, these are the examples, okay? And your A, I'm making as 6 by 5. So I want to add 10 minus 5, 0.2, making 6 by 5, that's right, minus 6, 7. You can do at home and practice it. 10, 100, 2, 3, 5, minus 20. See? Now, if you look at this Jacobian, say, what is Jacobian of matrix at a certain time, you have 6 by 5, meaning that your system, your robot has 5 degree of freedom, or 5 joints in space, if this is the Jacobian of your matrix. That's right. So now first you have to know the condition that I was talking about. I have to say rank of new A. See, this is the rank of the A. Oh, it says full rank column wide, because 1, 2, 3, oh, what the hell was that? So because 1, 2, 3, 4, 5 columns, so it's full rank column wise, or the columns are linearly independent. So if I use this formula again, look at here. Let me do this, and you can see it. Come on, okay. I don't know where it goes. Okay, if I use this formula again, this formula, because left pseudo inverses, right? Here we go. It's gonna be 5 by 6. That's right. So 5 by 6, see, 1, 2, 3, 4, 5, and 6. So based on whatever that we generalized for the 5 degrees, so suppose that you have 5 degrees of freedom robot in the space, so you're gonna be 6 by 5 Jacobian matrix. Your M is 5. Your M is 5. So Jacobian left Jacobian inverse, left pseudo inverse, sorry guys, gonna be I of 5 by 5. Here we go. So we're gonna have identity matrix of 5 by 5. See here? If I say AP in A, you're gonna have 5 by 5 unit matrix, identity matrix. 1, 1, 1, 1. See, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. If you have 4, you're gonna have 4 by 4. If you have 2, you're gonna have 2 by 2. Understand? So let me try 2 and then go to the point, because suppose that suppose this is 6 by 2. Let me do like this. You cannot see it because some technical difficulty, but now you're gonna see it. Bear with me. Here we go. This is 6 by 2, that's right. So if I say pseudo inverse, because this is if I say rank of this matrix gonna be 2, because you have 2 columns, so it means that the columns of this matrix are linearly independent. So the pseudo inverse, as we calculate, is gonna be 2 by 6. That's right. So if I calculate left pseudo inverse, it's gonna be 2 by 2 identity matrix, because your M is 2. So note the point is, so why we have to know this, because at the end of the day, x dot is equal to Jacobian matrix in Q dot. Now we have to know that your M is greater than 6, smaller than 6, or M greater than 6, means you have redundancy. You have the joints number is higher than the coordinates in space. Now I'm talking about this. That's not about what. Look at this is the Baxter-Lab. Baxter-Lab is like this. Okay. So if I know this, so if I want to find, if I have the desired trajectory of the vector, I have to use left pseudo inverse. I have to multiply the both sides from the left. I have to say left pseudo inverse. Now this case again, let me clear here. This case is when J is M, J Jacobian max is 6 by M, and the M is smaller than 6. Okay, so now we know that this is gonna be identity matrix of M by M. Understand? This is I. Now you can calculate the velocity of the joints based on the given information. Understand what I'm talking about? Okay. And this side, let me discuss this also. And this side, let me take this to the next page. So we got that if m is smaller than 6, you have the left pseudo inverse, right? So we got that finally q dot is equal to pseudo inverse of the j in x dot. But this side, if the suppose that, for example, suppose that m is equal to 2, for example. So q dot gonna be, so this what was becoming what? This is how much? This is gonna be 2 by 6. Remember? Look at here in the MATLAB. So pseudo inverse is gonna be 2 by 6. Or let me show it here. Or if you have 5 by 6, gonna be 5 by 6. So if you have 4 degree of freedom, gonna be 4 by 6 pseudo inverse of the left pseudo inverse. And the x dot always, if you're working in the 3D space, gonna be 6 by 1. So the result gonna be how much? Result gonna be this. Come on, 2 by 1. Means that because you have 2 degree of freedom, you have 2 angles. Gonna be theta dot 1 and theta dot 2. Here we go. Now if m is 5, means that you have 5 degree of freedom robot. So q dot is equal to pseudo inverse of the Jacobian, gonna be 5 by 6. So always this is 6 by 1. That's right. As we calculated in the previous class, part 15. What was that? Go see the code. Vx, Vy, Vz, omega x, omega y, and omega z. So you're gonna have 5 by 1, 5 by 1. 1, 2, 3, 4, 5. Because you have 5 joints, 5 degree of freedom. Here we go. Now you have theta dot, integrate that to get the theta. Simple like that. That's right. Simple like that. So now, but in MATLAB, it must be similar to that. In MATLAB, we have inv for regular inverse when your matrix is square, but we have p inv when you have non-square or pseudo inverse. This is for pseudo. Look at here. Where I wrote pseudo. Here we go. Left pseudo. Pseudo, first letter gonna be P. So P inv is the MATLAB. Like what? Let me do this. You don't need to guys calculate these each time for the left pseudo. Let me do this all of them. And suppose I'm taking to this example 6 by 2 that we need pseudo inverse. That's right. You're gonna only say, if you want to calculate left pseudo inverse or J transpose J, left pseudo inverse, from left is coming. You only type, get here, P inv in A. Means pseudo inverse, but from left in A. Gonna be, oh, what happened? Oh, why it in A? See, gonna be 2 by 2. Just write this, but from left. P inv in A means pseudo inverse of A in A. Pseudo inverse of Jacobian in A. Now look at here the other example. You have see, we have what? 6 by 5. A was 5 degree of freedom. You just type, let me do this. You just write P_inv again, P_inv of A multiplied by A. You're gonna have 5 by 5. So you did that left pseudo inverse. 1 1 1 1 1 0 0 0 0 0. You understand? So this is when the number of degree of freedom of the system is smaller than the number of degree of freedom of the robot is smaller than the coordinates or motions in space, in your space. Coordinates in space can be 2D space, can be 3D space. Huh? But the next topic is that we have in lab, Baxter robot, is when in Baxter that I showed you that I have in my dynamic system and control lab, when I have 7 degree of freedom robot. So I'm going to teach this in the next class. Okay.